Imagine you're an archaeologist. You dig down through layers of rock, deeper and deeper into the past, expecting to find simple stone tools, primitive shelters, the awkward early experiments of a young civilization. And instead, buried in the deepest, oldest layer, you uncover a fully built city. Marble columns, plumbing, public libraries. Something that, by every model you've ever trusted, should not exist for another 10,000 years. That, in essence, is the situation cosmologists have been quietly panicking about for the last 3 years. Because the James Webb Space Telescope, the most powerful infrared eye humanity has ever built, has been digging into the deepest layers of the universe, and it keeps pulling out galaxies that, according to our best physics, shouldn't be there. They're too big. They're too bright. They're too organized. They appear at moments in cosmic history when the universe should still have been a chaotic soup of hydrogen and helium, not a place that hosts mature, luminous, fully formed galaxies the size of the Milky Way. And the deeper Webb looks, the worse the problem gets. To understand why this matters, why this isn't just an obscure squabble between astronomers, but a genuine crack in our picture of the cosmos, you need to understand the story we thought we knew. For decades, our model of galaxy formation has rested on a fairly elegant premise. After the Big Bang, the universe was almost perfectly smooth. Almost. There were tiny quantum ripples, fluctuations in density so small you could barely call them anything at all. Over hundreds of millions of years, gravity slowly amplified those ripples. Dense regions pulled in more matter. Dark matter, that invisible, ghostly scaffolding that outweighs ordinary matter by a factor of 5, clumped first, forming vast cosmic webs. Hydrogen and helium gas, drawn into those gravitational wells, eventually collapsed, ignited, and gave birth to the first stars. Then those stars gathered into the first galaxies. Then those galaxies merged, and merged again, and gradually, over billions of years, grew into the spirals and ellipticals we see today. Slow. Hierarchical. Bottom up. That was the story. And it predicted something very specific. If you looked at the universe just 300 or 400 million years after the Big Bang, a cosmic infancy by any measure, you should see only the tiniest, dimmest, most chaotic baby galaxies. Little smudges of gas and a few thousand stars. Hardly anything worth photographing. Then Webb opened its eye. In late 2022, just months after the telescope began returning data, astronomers started reporting something strange. They were finding galaxies at extraordinary distances, meaning extraordinarily early in cosmic time, and these galaxies were not the timid little smudges anyone had expected. They were huge. They were luminous. Some appeared to contain tens of billions, even hundreds of billions of stars worth of mass, packed together at a time when the universe itself was less than 5% of its current age. One of the most striking discoveries was a galaxy called CRS 93316, initially flagged at a redshift of around 16, meaning we were seeing it as it existed roughly 235 million years after the Big Bang. That's barely an eye blink in cosmic terms. And yet there it sat, glowing brightly enough to be detected from 13.5 billion light-years away. Then there was Jade's GSZ 14-0, confirmed at a redshift of 14.32, observed as it was just 290 million years after the Big Bang, a galaxy already nearly 2 billion solar masses, much more compact and luminous than models predicted. And these are not isolated cases. Webb has now found dozens of these so-called impossibly early galaxies. The technical term that started appearing in papers was as understated as it was alarming. Astronomers called it a tension between observation and theory, which is scientist speak for something is broken, and we're trying to figure out what. Now, there's an important caveat here, and I want to be honest about it. Measuring the mass of a galaxy 13 billion light-years away is not like weighing a bag of flour. We don't see the stars directly. We see the light those stars emit, redshifted into the infrared by the expansion of the universe, after that light has traveled for almost the entire age of the cosmos. From the spectrum of that light, we try to infer how many stars are there, what kind of stars they are, how old they are, and how massive the whole system must be. Every step of that chain has assumptions baked in. So when Webb finds a galaxy that seems too massive for its age, there's always a chance, a real, honest scientific possibility, that we're misinterpreting the data. Maybe these galaxies host active supermassive black holes whose intense radiation is being mistaken for starlight, inflating our mass estimates. Maybe the early universe forged stars that were much more massive and much more luminous per unit mass than the stars we see today, a so-called top-heavy initial mass function that would let a smaller pile of matter shine as brightly as a much larger one. Maybe dust in the early galaxies is doing something we don't understand. Each of these explanations chips away at the problem, but none of them, so far, makes it disappear. Because even after every correction astronomers can reasonably apply, the picture that emerges is one in which galaxies in the early universe grew faster, brighter, and more abundantly than the standard cosmological model known as lambda cold dark matter, or LCDM, predicts. Some studies suggest the discrepancy is a factor of 10 or more. There simply isn't enough ordinary matter inside the dark matter halos of the early universe to assemble these galaxies that fast, unless almost every atom of available gas converted into stars with near-perfect efficiency, which, frankly, is not how galaxies work. Real galaxies, even today, convert only a few % of their gas into stars before feedback from supernovae and radiation blows the rest away. So what's actually going on? This is where things get genuinely interesting, because the possibilities range from the mundane to the cosmologically radical. On the mundane end, perhaps our models of early star formation are simply too conservative. Perhaps in the dense, metal-poor, gas-rich conditions of the early universe, stars could form in furious bursts, with feedback playing a smaller role than it does today. Perhaps the first stars were so colossal, hundreds of times the mass of the Sun, that even small numbers of them lit up the early cosmos like flares in a cave. This is uncomfortable for theorists, but it doesn't require rewriting physics. It just requires admitting that our simulations have missed something about how matter behaves in the first cosmic dawn. But there's another possibility, the one that keeps a quieter, more dangerous fire burning at the edge of cosmology. Maybe the universe itself was different in a way our standard model doesn't allow. Maybe dark matter isn't quite the simple, cold, collisionless particle we've assumed. Maybe the expansion of the early universe didn't proceed at the rate we've calculated. Maybe gravity itself, on cosmic scales, behaves in ways general relativity hasn't fully captured. Each of these would let galaxies form earlier and grow faster, but each would also force us to reconsider the fundamental scaffolding of cosmology. Decades of work would need to be retested. Textbooks would need rewriting. The smooth, confident picture of a universe that began 13.8 billion years ago and grew up in an orderly, hierarchical fashion would suddenly need to be replaced with something more wild. Most cosmologists, being cautious by nature, are betting on the mundane explanations. And they're probably right, at least in part. But what's striking is that as Webb continues to look and as follow-up spectroscopy continues to confirm the distances of these strange early galaxies, the problem isn't shrinking. It's stubborn. It's persistent. It's the sort of anomaly that, in the history of physics, has occasionally turned out to be the first whisper of a revolution. Think for a moment about what this means in human terms. For most of the 20th century, we did not know what the universe was, where it came from, or how old it was. We figured it out, painstakingly, generation by generation, using telescopes that grew larger and instruments that grew sharper. By the early 2000s, we believed we had the broad outline right. The age of the universe. The proportion of dark matter, dark energy, and ordinary matter. The cosmic microwave background, mapped in exquisite detail. We had built a cathedral of cosmology, and it stood. Then we launched a telescope 1,000,000 miles into space, opened its golden eye, and aimed it at the deepest darkness we could find. And almost immediately, the cathedral began to creak. It's worth pausing on that. The standard cosmological model is one of the most successful theories in the history of science. It predicts the ratio of hydrogen to helium produced in the first few minutes after the Big Bang to extraordinary precision. It explains the patterns in the cosmic microwave background. It accounts for the large-scale distribution of galaxies across billions of light-years. It is not wrong in any obvious sense. It is, at worst, incomplete. And the early galaxy problem may be the first hint of where that incompleteness lives. What makes this particular anomaly so unsettling is that it's not a faint statistical signal buried in noise. It's a direct image. You can look at the web data with your own eyes, pixels of infrared light captured by a telescope orbiting the second Lagrange point, and see structures that, according to our best understanding of how matter and gravity work, should not have had time to assemble. The disconnect is visible. It's tangible. It's there, in the photographs. And here is the strangest thought of all. When we look at these galaxies, we are not looking at the present. We are looking 13 billion years into the past. Whatever those galaxies are now, whether they grew into giant ellipticals, merged with neighbors, or were torn apart by collisions, they exist today, somewhere out in the unreachable distance, transformed beyond recognition. The light we are confused by is light that was emitted before our solar system existed, before our planet existed, before there was any structure in the universe that could one day be looked at by curious creatures wondering how it all came together. The tension Webb has revealed isn't just about numbers in a spreadsheet. It's about the question that the marble columns in the deep dig represent. How did the universe build itself so quickly? Because if those early galaxies are real, and if they are as massive as they appear, then the cosmos was not the slow, patient, gradual machine we imagined. It was something faster, hungrier, more capable of organizing matter into structure than our equations allow. Something that, in its earliest moments, was already busy doing things we don't fully understand. Maybe in 5 years, the solution will be a quiet revision to our star formation models, and the problem will dissolve into a footnote in a graduate textbook. Or maybe, and this is what keeps cosmologists awake, these impossible galaxies are the first real evidence that the universe we think we live in is not the universe we actually live in. That somewhere between the Big Bang and the first cosmic dawn, physics did something we have not yet learned to describe. The marble columns are there, buried in the deepest layer of the dig. We can see them clearly now. The question is no longer whether they exist.